to additive manufacturing and 3D printing using Ansys SpaceClaim. This is week 5, in which we'll be covering designing parts for 3D printing. Last week, we covered the 4 major 3D printing technologies that you would most commonly find. Selective laser melting and sintering, which uses a laser to melt metal powder layers into a finished piece. Fused deposition modeling, which uses thermoplastic filament melted through a hot end and extruded onto a build plate in a layer-by-layer motion to build the finished piece. Sterile lithography, which uses UV curing resin hardened by a UV laser shown through the bottom of a glass tank, manufacturing the end piece in a layer-by-layer fashion onto a build plate that's slowly pulled out. And last but not least, laminate object manufacturing uses the gluing of laminated sheets on top of each other in a layer-by-layer fashion, where each layer is cut into the desired shape by a laser shown from above. However, in this week, what we're going to cover are 3D printing limitations of each of the technologies that we've discussed. Some of these being how the build direction of parts affects the speed of manufacturing the part and the end strength of the piece produced, and how we can orientate parts in SpaceClaim suit our needs for the end piece. Another issue that we'll be discussing is steep slopes and overhangs, for which we'll look at using supports to overcome some of these limitations. And lastly, we'll also cover contact area with build plate issues, such as in an example where when we're building a design and it doesn't have much area in contact with the build plate on the base layer, this can result in a few adhesion issues. However, we'll look at how we can overcome these issues using brims. After we discuss the issues and how we can resolve or alleviate some of the issues, we'll be looking more into detail on how we can design our pieces or design for these issues so we don't have them using 3D printing. We'll also look at what infill is, the iterative process when 3D printing, and post-processing after printing is complete. We'll also look at slicing software that prepares the 3D models before they can 3D printed, some of the more common file types for files that you'll find when you are 3D printing, and at the end of this course, we'll also be having a final project. The learning objectives for this week: to learn about some of the printing issues that you may come across when printing your part, some of the techniques and tools that you can use when 3D modeling to overcome some of these 3D printing issues, how you can design parts specifically designed to be 3D printed, that is, designing with 3D printing in mind, and you'll understand how 3D printing works from a process flow perspective, from start to finish, and the different file types needed at each stage. So let's begin. 3D printing limitations. There are quite a few limitations to what and how objects can be made using 3D printing. Some of these limitations include the build direction, so that is layer orientation, the direction in which we build our pieces using the layer-by-layer method. This can affect the structure of the parts, such as strength. We'll also discuss some of the problems with steep overslopes and overhangs. This is where we can introduce some support structures to alleviate this in the design stage. Also, some issues that you may encounter are having a good contact area with the build plate, because if you don't have this, either the piece being printed could be knocked off the 3D printer, or you can have adhesion issues and the piece may come off just through the motion of the build plate or the build head. We'll look at how we can use brims to alleviate this issue later on. And lastly, considering surface finish or some additional structures that had to be added to support the piece being printed or to alleviate some issues previously discussed, post-processing may be required where once 3D printing is completed, we might have to sand the surface of the object to achieve a smoother finish or remove some of the support structures that were assisting during the printing process. Let's dive deeper into the build direction of the parts and how this can affect the speed and the strength. As we know, as we've covered previously last week, 3D printing is a layer by layer process. So we start off with the base layer and add on top of that layer by layer until we end up with our finished piece. Considering this layer by layer process, it is important to take note that the bonds and structures within a layer is much stronger than in between the layers. So if, let's say, you have a model that you want to 3D print and you split this model up into 100 layers, the strength between layer 1 and 2 would be less than the strength within layer 1 itself. This is because mostly in most 3D printing applications, you have to heat or melt some of the material in points or in a layer before you can add another layer on top of that. So considering within a layer, there's much less time for the piece to cool down. And as you are melting a certain point, it also heats up the surrounding geometry. The adhesion within the layer or the melting within a layer can occur better than in between layers because there's that delay for the 3D printer itself to shift to the new layer height to add on top of it. That's a lot of detail, but as long as you understand that within a layer strong, in between layer less strong, you should be good. However, this means that tensional or pulling strength along a build direction will be weak, but perpendicular to the build direction, the strength will be high. So, if we look at an example, this can make a bit more sense. Imagine you are building or fabricating a hook for a device, a contraption, or application of your choice, and this hook is meant to be designed to lift a weight. Right? So if we look at this hook over here on the right, in image A, you can see that we've built it with the bottom of the hook facing down and the top of the hook facing up. So it's standing vertically. If you look at the cross section over here, you can see that the layers are horizontal, or the layers are built up from bottom of the hook to top of the hook. So within a layer is sideways from left to right. However, in between layers is from bottom to top. Considering if this hook is meant to support a load, the load would be pulling straight downwards on the hook. This might have an effect of trying to peel the layers from each other. And considering the adhesion between layers is low, there is a high chance or a high risk of this design failing its purpose. However, if you look at image B, where we've orientated the hook on its side or laterally instead of vertically. When we build the layers, the layer orientation now is along the hook, from the bottom of the hook to the top of the hook. Yeah. And the layers are built in the direction from right of the hook to the left of the hook, or vice versa. But this means that when we attach a load to the bottom of the hook, is going to pull along the layer direction. And this would mean, considering that the strength within a layer is strong, it has a less of a chance to break. And most definitely it'll be better suited to supporting a load than the orientation as described. We have also mentioned that the build direction of the parts can affect the speed of the print. So what does that mean? How can the orientation or the direction that we build the parts affect the speed of the print, considering that the parts would theoretically have the same volume? So we are not creating a bigger piece, we are creating the same piece. So what adds to the time? Well, this is because generally printing a layer is much faster than transitioning and printing several layers. That's because 3D printers, they have to stop printing a layer, shift to a new layer height, and then start building the second layer on top of that. And this takes far more time. Pretty much, if we look on the bottom, we have one hook oriented vertically, and to the right of that, we have one hook orientated on its side or laterally, as per our previous example. If we were to split the hook on the left into layers of a certain thickness, let's say 0.5 millimeters, and the one on the right into layers of thickness 0.5 millimeters as well, then obviously the one on the left would have more layers because it's taller, whereas the one on the right would have less but much wider layers. So pretty much, considering that usually the build head, and that's creating the parts, or the laser that's melting the material or curing resin or whatever, the build head, it can move and sort of build a layer much faster than when it has to transition to another layer. So it's that transitioning time that adds up between the layers. So the more layers that you have, the more transition time that you have, adding to the final time. If you have less layers but bigger layers, it's still much faster to work within a layer than in between layers. So your time is reduced. So pretty much considering this, the taller or the larger the object is in the build direction, the slower the 3D print or build will be. Whereas if it's much shorter in the build direction, or if it has less layers, yeah, one is analogous to the other, the print speed will be much faster. It will take you less time to end up. Now let's see if we can have a look on how we can change the orientation of our parts in SpaceClaim. So if we go back to our example of the hook and try to just create a quick hook for demonstration purposes, using some of the tools that we've already learned. where you start from simple geometry and you just work your way up from there. Right now I'm just creating a few rounded corners. You can also do this with fillets if you've already created the geometry. Considering the amount of tools that SpaceClaim offers, there are many different ways to create your geometry. If you double click on an edge, it selects all the edges around the perimeter. That's just a little hotkey or top tip when you're playing around with geometry. There we go. So in a few minutes, we can end up with something like this. This is how I've designed the hook. If you've been practicing the tools that we've covered up to now, this should be relatively quick and easy for you. So right now, you can see we've built the hook in the YX plane. So when you end up printing it, generally you print pieces along the Z-axis, or that's how they end up being orientated. Let's say we actually wanted to build the hook vertically along the Z. Yeah? Or we wanted to change the orientation. How would we go about this? Well, first we'd have to select the whole hook. How do you select the whole body? We've seen how to select the face, how to select an edge, maybe how to select edges around the perimeter by double clicking. Well, if you triple click a body, it should select the whole solid body. Yeah, there you go. Now that you have the whole body selected, you can click on the Move tool that we've covered previously. This adds a set of axes to our model. Now, if you can see right here, our model is in the XY plane. We want to rotate it along the X arrow or X axis, so this face can face vertically upwards. Considering we want to rotate it along the X axis, which is the red one, we click the red arc to go around. And considering we built it flat, we only need to move it to 90 degrees. You can just type that in if you wish. And now this has rotated and reorientated our model in the Z axis. So pretty much what we have is our model orientated. If we click along the Z, it lies straight over here. Okay, so let's see. We've covered the triple clicking the body in order to select the whole model. The axes that appear, clicking on the arc and rotating. Also, considering this, you're not limited just to rotating. You can also move the body. If you click on an axis and drag, you move it along that axis. So we can move it along Z, along Y, along X as well. Any of these axes, we can move our model along there. It's not just for moving around features. Okay,